There we go. Hi, everyone. Let's take a look at the sample test for organic chemistry, the exam on spectroscopy. Okay, so this exam is going to be much different from other ones. You know, the other exams had reactions and mechanisms, sometimes multi-step synthesis, and the bulk of the test was testing your knowledge of what you knew about reactions. Did you have the reagents memorized? Did you know how they work? And then applying it to a certain situation. Okay, this test is more about your skill, so it definitely takes some practice. So here's some problems to help us get that practice. Okay, so I cut and pasted a few of the sample problems on here, and I picked these because I thought they're a little more complicated than some of the others. Not necessarily that what I'm not saying that very clearly. I picked problems I thought would be helpful to clarify the answer key on the sample test. There are other problems that I'm not covering here that are just as important. In other words, they can show up on the exam even though I don't discuss those problems here. I didn't discuss them here because I think the answer key is pretty straightforward, or students haven't been asking questions about them. Some of these problems I'm going to deal with today, there's a little bit of detail or something a little weird about them. So let's clear that up. Okay, get the pen going here. Ooh, we're all set. Okay, so I started with number 3 on the sample test. Write 2 possible chemical formulas for a compound composed only of carbon, hydrogen, and 2 oxygens with a parent ion of 156. I feel like I want to just get started, but let's see the rest of the question. Draw 3 possible structures. For full credit, any functional group containing oxygen must appear only once among your 3 structures. All right, let's just clarify that. That's I remember why I wanted to pick that one. You are told that your chemical formula must contain 2 oxygens. And I want to see your skill at using different functional groups of oxygen. So to get full credit, every time an oxygen shows up in your molecule, you got to change it to a new functional group. So there's 2 oxygens. So if you have a molecule with 2 alcohols, yikes, you just repeated the alcohol group. You can't repeat. Not all the problems are going to be like this, but sometimes they will. Okay. All right. So that's the first point I wanted to make. And then we'll just kind of go through the procedure. If you're given a mass spectrum, mass spec, you know, we're supposed to go and find out its parent peak. Well, that process was done for us already. And then normally we divide by 12 to find out how many carbons could possibly be there. And then you could subtract out 16 mass units so you could bring in an oxygen. This time, however, we're told you got to have 2 oxygens. And you get a periodic table on every exam. So slide over here to the periodic table. There we go. Look up oxygen, and the atomic mass is 15.9994. And the trick you can use is if you round off your atomic masses, then you're close to the most common isotope. So oxygen is element 8 protons, and the most common variety of oxygen, the most common isotope, is oxygen that weighs 16 mass units. Or in other words, it has 8 neutrons in it. That's just a cool little trick. So we're assuming we're using the most common form of oxygen in our molecules. So they're going to weigh, each oxygen will weigh 16 mass units. But we're going to have 2 oxygens. So 2 times 16 is 32. So let's subtract that out. And you don't get a calculator, but hey, it's all about skill. So let's just see your math skills here. Show your work. In case you make a mistake, I'll take off a point and maybe half a point, depending on the problem. And then I'll see what you do with the rest of it, so you can still earn partial credit. But of course, try not to make those mistakes, and I'll try too. 6 minus 2 is 4. 5 minus 3 is 2. And that 1 comes down, 124. Okay, so I took care of the 2 oxygens. Now, of the remaining 124 mass units, let's see how many times carbon can show up. Well, long division, 1 times 12 is 12, and then there's 4 left over. It doesn't divide in there, so 10, right? 0 times 12, can't subtract it. Okay, so the simplest formula with 2 oxygens would be 10 carbons, 4 hydrogens, ew, that's not very many hydrogens. And then we're told 2 oxygens, I already took care of that. If you have time, you should double check your math. Okay, so does this formula add up to 156? I got 10 carbons, so that's 10 times 12, 4 hydrogens, that's 1 times 4, and that looks like the letter D, it's supposed to be an O. And then 2 times 16 is 32. So 120 is 12 times 10, and 4, add that up, I'm going to get a 6, 156. Yeah. Okay. So good. My math looks good. I don't like this formula. And besides, the question's asking me to propose 2 chemical formulas. So one trick you can use is, hey, let's bring in more hydrogens. We can't change the mass. It still has to add up to 156. So the cool trick is you can bring in 12 hydrogens if you subtract 1 carbon. Carbon weighs 12, and 12 H's also weigh 12. So bring in 12, take away 12. The mass will still have to 156, but now your formula can be C9, H16O2, and that's a much more reasonable distribution of hydrogens per carbon. It's about a little less than twice as many, but that sounds reasonable. 4 hydrogens with 10 carbons, yikes, that is really low on hydrogens. You can draw molecules that work. They'll be very challenging though. And if this had other other data, and it was actually proposed the correct structure, this formula is going to be pretty unlikely because it is so unusual having so few hydrogens. So this is a better one. I had a student ask me about just the way this question is phrased, and she made a good point. I interpret this problem to say, hey, propose 2 chemical formulas, and I did, and then draw 3 possible structures. Okay, so what I don't mean is draw 6, 3 for each. No, you need 3 total. And then you decide, do you want to draw 1 structure from this formula and 2 from this one? Do you want to do 2 of these and 1 of those? Or do you want all 3 of your structures from this one? Your choice, whatever you're most comfortable with. And I think it'll be easier to draw all 3 structures of this formula. All right, so to get a structure quickly from your chemical formula, count up the degrees of unsaturation. And then you'll have to remember that formula. So there's some memorization on this exam, even though it's not mechanisms or reagents. You got to remember the number of hydrogens that are possible if it's saturated is 2 times the number of carbons, 9, plus 2 more. And then you need to subtract your actual number of hydrogens, 16, and then adjust for any halides or nitrogen. There are none here. And you can ignore the oxygen, counts as 0. The letter O looks like a 0. That's how I remember it. And then you have to divide the whole thing by 2. Excuse me. 2 times 9 is 18, plus 2 is 20. 20 minus 16 is 4. 4 over 2 is 2. We have 2 degrees, and that means the molecule should have 2 rings, or 2 pi bonds, or 1 ring and 1 pi bond. Cool. All right, so that gives us some ideas for drawing those 3 structures. The other thing to remember, the other requirement is every time you put an oxygen in the molecule, identify what its functional group is and don't repeat it. Okay. The formula has to be C9, so maybe I'll take the simplest route. How about just 9 carbons in a row? 1, 2, 3, 4, 5, 6, 7, 8, 9. I gotta get 2 degrees in here. So how about a pair of double bonds? 1 degree, 2 degree, good. And then I got some oxygens and hydrogens. Okay, the hydrogens should take care of themselves. as long as I count the carbons correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I got the degrees correctly. Yep, 2 degrees, 2 pi bonds. And I'll stick in the oxygen. So maybe I'll make this the alcohol. And then I can't use the alcohol group again. So maybe what I'll do is, well, if I change this carbon to an oxygen, so I have an ether. And if I just removed a carbon effectively, right? So let's put the carbon at the end of the chain, maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Good. And this should work. That's my first of 3 structures. And now I can't use an alcohol or an ether in any of my remaining structures. That could be challenging. Unless you remember that oxygen can make double bonds. And then we have aldehydes, ketones, carboxylic acids, esters, amides. Oh, no nitrogen, can't do an amide here. Yeah, so how about an ester next? And then, or if you want a ring, you can get some variety, or you don't have to. Just make sure you draw a different molecule. So if you want to keep going straight chain again, there's 1, 2, 3, 4, 5, 6. Maybe I'll throw in the double bond and the O for an ester. So that's 1, 2, 3, 4, 5, 6 carbons. Here's number 7, 8, 9. And I'm done. Wow, 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got 2 O's. Ooh, I only have 1 pi bond. Whoops. Bring in a second pi bond. I don't know, double bond, maybe here or anywhere. Cool. And then I need one more structure. Can't use an ester, can't use an alcohol, can't use an ether, so maybe a carboxylic acid. And hey, how about if I put a ring? Don't have to. How about if I put a ring of 6, put the carboxylic acid out here? There's lots of possibilities. Oh, how come I drew in that H and this H? Because skeletal drawings are drawn where you can only remove the hydrogens when they're attached to carbon. But the oxygen here is not carbon. If you want to show all the bonds to the oxygen, you have to include the hydrogen. All right, I got 7 carbons in this molecule so far, so I need 2 more. There we go. I got a ring and a pi bond. That's my 2 degrees on saturation. That should work. 6 carbons in a ring, 7, 8, and 9. 2 oxygens, we're good. And there's lots of other molecules you could draw for full credit. But once you're done with this one, just double check your functional groups: carboxylic acid, ester, ether, alcohol. We could have had an aldehyde. We could have had a couple, a ketone. So there's other structures that could have been drawn for full credit. All right, that's number 3. Reading it over, make sure I didn't forget anything. I think we're good. Number 5, jump down to number 5. Explain how you could use infrared spectroscopy to differentiate between 1-chloro, 2-methyl, cyclononene, and 2-chloro, 3-ethyl, 4-octine. And then I thought, well, let's just go get the correlations chart for IR. So on the actual exam, you'll have 3 correlation charts. Well, maybe that was the first of them, sorry. Here we go. So I honestly haven't made the sample the actual test yet, so I don't know what order I'm going to put these. But maybe I'll put hydrogen NMR first, and you can see that H1 right here. That'll to remind you, oh, this data is regarding the hydrogen NMR. And then here's the carbon. How do you know? The scale is about 200. It says chemical shift. That's this x-axis for NMR. And if the x-axis goes to around 10 or 12, that's hydrogen. But this goes out to 200 or so. It's for carbon. And the third one is the IR, which actually says IR. So maybe by process elimination, you figure out which one's carbon. This one's IR. This one's hydrogen NMR. So this other one right here must be carbon. Those are your 3 correlation tables. Cool. And then what we can do is look at the functional groups, because that's what IR, there you go. IR is really good at identifying functional groups. So if you want to differentiate, it just means tell them apart. Maybe what happened in the lab is you had two bottles and the labels fell off. And you went up to the shelf and there's the two bottles sitting there and two labels are on the floor. And you pick up the two labels. One label says this, the other label says that. And you decide, okay, why don't I go take a little bit of this molecule and put it in the IR and get my data? What are you going to look for in terms of peaks that says, aha, the IR spectra says that it's this molecule? Or, aha, what are you going to look for that says it's this molecule? So you're looking for something different. So what's different in terms of functional groups? Well, they both have chlorine, so that's not going to help. There's an ethyl and a methyl, so that is different, but they're both alkane functional groups. So if you look here, there's no data for a methyl versus ethyl, and so nope, that's not going to help. 9 versus 8, no, that's alkane. So it's really here about ine, the carbon-carbon triple bond, versus the ene, the carbon-carbon double bond. And so you can come over here and realize, hey, here's the alkene and here's the alkyne. And so you get more points for more details. So if someone said, use IR to see the difference between triple bond and double bond, partial credit. If someone says, look for all of these peaks to tell you if it's an alkene, or all of these peaks to tell you it's an alkyne, more partial credit, but not full credit. So what's really going on? This ene is here, and so it's possible for alkenes that you could have peaks at a little bit beyond 3,000 and around 1,700. Well, I know, 1640 to 1680. All the alkenes will have a carbon-carbon double bond, but do all alkenes have a hydrogen on that alkene carbon? Or more importantly, does this one? So you might want to sketch the molecule. So it's cyclononene. So it's a ring of 9 carbons. So I don't know, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'll call this number 1 and this one 2. So attached to number 1 is a chlorine. Whoops, off the screen. There's my double bond. And on number 2 is a methyl. So this alkene carbon has a chlorine and a carbon. This carbon, alkene carbon, has a methyl and the rest of the ring. It doesn't have a hydrogen attached to the carbon. So that's not seen here. And if you put that in your answer, then you're earning more points. So look for this. And then say it's not going to be seen, so don't bother looking for a peak just to the left of 3,000. You're not going to find one for this molecule. And then also for full credit, what are you going to be looking for to identify this molecule? The triple bond. And the triple bond could be here, so look for this. And then do you want to look for this hydrogen also? Because if it's possible, you'll get credit points for saying yes. Let's go and look. Well, the triple bond shows up on carbon 4 of 8 carbons. This triple bond's in the middle of the chain. To have a hydrogen, the triple bond has to be at the end of the chain. So no, this is not going to be seen. And so you earn some points for saying, I can't see this in this molecule, 4-octene, because the triple bond does not possess a hydrogen. So you can't see this peak. It's not going to be there. It's only there if the triple bond carbon has a hydrogen. Cool. So basically just talking about these 4 things specific for your 2 molecules would be enough. There we go. That was number 5. What's next? 6. And then 7. I got them grouped together. How come? Well, let's look at it. 6 says, for each of the compounds below, tell how many signals you would expect the molecule to have in the carbon NMR and in the hydrogen NMR. Keyword is signals. In number 7, it says, predict the splitting patterns you'd expect for each proton in the molecules below. Which element is a proton? Hydrogen. I know all elements have protons in it, but this is a single proton. So which element only has one proton? Hydrogen. Okay. Biggest difference is splitting patterns being asked here and signals up here. This basically is asking for the number of peaks, how many signals. It really wants the number of peaks. And you want to ignore splitting. It's a way of telling me that you understand when atoms can be equivalent in the NMR. So let's do A over here. So let's look at the carbon. So how many carbons are here? There are 5. So you're going to get a peak from this quaternary carbon. I'll just call it peak A. And then this methyl group, this carbon of the methyl group is going to produce a second peak. I'll call it B. And then there's a plane symmetry here, right? So this methyl is equivalent to this one, meaning both carbons produce peaks, but they'll stack on top of each other. They both produce a peak. They'll stack on top of each other. And so it'll appear as though it's one big peak. So this carbon will also produce the same peak at the same position. They'll stack up on top and be really tall. There's also a mirror plane here, which means these two methyls are also equivalent. We have a total of 4. No, we don't. We have a total of 2, just a peak A and a peak B. We get 2 signals or 2 peaks in the carbon. I really messed that up with all my scribblings. So let's redraw it here and talk about the hydrogen NMR now. In the hydrogen NMR, every hydrogen atom gives a peak. So this carbon is not going to produce a peak in the hydrogen NMR. It's invisible. Only these 12 hydrogens would produce a peak. But we just talked about how they're all symmetric, all equivalent. So these 3 hydrogens are equivalent to each other because they're attached to the same carbon. So all 3 are going to stack up, produce a peak. And then the symmetry plane here, so all 3 of these are going to be equivalent to that one. And there's a symmetry plane here, which means the others are also equivalent. So there's only 1 peak or 1 signal in the hydrogen NMR. Let's go down here and do this last one. What's the splitting pattern? Okay, well, splitting patterns are only seen in hydrogen NMR. So ignore the carbon, and of course, ignore oxygen and chlorine. They don't produce peaks in either the NMR of hydrogen or of carbon. They're not carbon, they're not hydrogen. They won't produce a peak. So we got this hydrogen that's at the end of the chain, attached to a double bond, same carbon as the chlorine. This carbon is within the chain, so that's a different hydrogen, even though it's attached to an alkene. So if I was counting signals, I would say, hey, this is hydrogen A, and here's hydrogen B, but I'm not. We're looking at splitting patterns. Splitting patterns tell you how many neighbors are next door. So, and neighbors produce n+1 split peaks, right? So let's ask, hey, hydrogen, do you have any neighbors? Well, what house do you live in? You live in this house, this carbon. So go next door, there's a chlorine, no H is there. Go next door to this carbon, hey, there is a H here. So your next door neighbor, there's in any direction from where your house, this hydrogen's house, there's a carbon there, 1 neighbor. So 1 neighbor produced 1+1 or 2 split peaks. 2 peaks is a doublet. Okay, so be very careful, read the question carefully. When asked for signals, your answers are going to be numbers. one peak, two peaks, one signal, two signals. But when it says splitting patterns, your answers are going to be doublet, or let's do this one. Hey, hydrogen, do you have any neighbors? Well, I live in this house. Next door, there's a carbon and an oxygen there. Nope, that's not hydrogen, no neighbor there. How about down here? Ooh, yes, there's a neighbor. So this hydrogen also has one neighbor. It also will be a doublet. And then how there's hydrogens here, look next door. They only have a carbon. There's only one house next door to their house. And that carbon doesn't have any kids living there, no H's. That's how I figured it out, how I think about neighbors. Anyways, these hydrogens don't have anyone to play with next door. They have zero neighbors, so it produces 0 plus 1. It just produces a normal peak, a singlet. There you go. Cool. Yeah, and so take a look at the answer key for other questions, to solve the other ones, but it's the same idea. Just pay attention to the question when you're talking about carbon. Make sure you identify every carbon, because every carbon will produce a peak. And then when it says H1 or splitting pattern, look at every hydrogen. Every hydrogen produces a peak. Okay, what does 8 look like? Or did I do 8? We finished with number 6 and 7. Nope, we're going to jump to 10. Cool. The question actually tells you it's a mass spectrum, but don't rely on that. The question may not actually tell you what you have. So when you look at this, I see a bunch of bar graphs. And the scale runs normally from 0 on the left side and increases towards the right. Ooh, the x-axis is also identified as M to Z. Those are all useful hints that say it's a mass spectrum. Okay, so it's not IR, it's not NMR, it's a mass spec. Okay, question A. Which halide is indicated by this mass spectrum? Okay, so in the video on mass spec, there were 3 elements we made a particular note about. Nitrogen. When nitrogen shows up in odd numbers of nitrogen, usually you just have one nitrogen in your molecule if there are any nitrogens. Your parent peak will have an odd number. Okay, so that's something to take note. If you find a parent peak and it's an odd number, that suggests that nitrogen is present. The other 2 elements were halides, bromine and chlorine. So chlorine, it's kind of nice they tell us this, but this may not be always given to you. Chlorine exists as 2 isotopes, so you should know that. You don't necessarily have to know the mass value. You can figure it out from the periodic table. Chlorine has mass 35.4527, so round that off to the nearest whole number, it's 35. So the most common isotope of chlorine is 35. And that's actually what they tell you here. Hey, chlorine occurs as chlorine 35, 75% of the time, 75.8. And then chlorine 37, 2 mass units higher, 35 up to 37 is 2 mass units. That happens 24, roughly 25% of the time. Bromine is 79 and 81, also 2 mass units apart, but they're nearly equal, nearly 50% abundance, or what's the word? It's like it's equally common. How often does it come? The probability of bromine showing up in your molecule that's bromine 79 or bromine 81 is about 50-50. And then if you didn't know it was 79, well, then you go and look over here, and I think this one doesn't quite work. Yeah, since it's 50-50, 79 and 81, if you round this off, you get 80, which is the average of 79 and 81. So you kind of have to know that bromine is the 50-50 one. And when you round off to 80, you realize, oh, wait, it's not 80. That's an unusual isotope. The common isotopes are 79 and 81, not rounding this off to 80. Okay, so I need you to remember those 3 elements, nitrogen, chlorine, and bromine, and their characteristics on the mass spec. When nitrogen's present, you get an odd number. When chlorine's present, you get this 3-to-1 ratio. There are 2 mass units apart. 3-to-1, well, One chlorine is 75% of the time showing up, and the other chlorine is 25%. 25 compared to 35, that's 3 to 1. And what does that mean? Well, here we have two peaks, and this peak is about 1/3 of this peak. It's a 3 to 1 ratio. This peak to that peak, and they're 2 mass units apart. You know what? We should double check that it really is 2 mass units. Do you remember the trick? The trick is to go down here in the fragmentation pattern and look for a region that has a lot of peaks. They're really weak, but I think this is a good region right here. So from here to there. So where am I? Well, this is 40 and this is 80, so halfway is 60. And now I got 60 right here, and then halfway is 70. So this is 70 and this one's 80. Okay, and then if you look really careful, be careful in the exam. Students are telling me if they try to zoom in on the exam, sometimes Proctorio will kick them out. If that happens to you, go back in the Canvas, look up the Canvas help troubleshooting page, and you'll find phone numbers and a web address so you can contact Proctorio, who should help you get back into the exam. Okay. Okay, so don't zoom in with the computer, zoom in with your face. Come in really close. And you know what? On the real exam, that's what you'll have to do. But this is a video. I'm trying to illustrate something. So I know it's kind of unfair because you won't be able to do this on the exam, but I can hit the zoom button. And now what you're looking at, hopefully if you're just looking at this video on your phone, maybe you can see it now. There's a little bump right there. Another one there, there. And you know what I should do is start counting. I'm going to start at 70. The next one is 71, 72, 73, 74, 75, 76, 77, 78, 79, and 80. Yes, so I verified that these are all 1 mass unit apart. And the spacing that you see here is a spacing throughout. So as you look at maybe this peak right here versus that one, get familiar with that distance. That's 1 mass unit. Let's go back to normal size. I know, so it's pretty tiny now, but now you have an idea that, yeah, the spacing between these are 1 mass unit. Each one of these separated 1 mass unit. So now for this one and that one, that's not 1 mass unit, it's actually 2. I can see a little peak in between. So yes, they're 2 mass units apart in a ratio of 3 to 1. That means this molecule contains chlorine. And that answers question A. Go back in the homework, and maybe in the video, there's an example somewhere of what happens when bromine is present. And you don't see a 3 to 1 ratio, you see a nearly 50-50 ratio. And they're 2 mass units apart. So that's how you identify bromine. Okay, so question A says, which halide is present? The answer is chlorine. How did you arrive? You could say, I found a pair of peaks, or just say 2 peaks that are 2 mass units apart in a ratio of 3 to 1. And you don't have to use this exact phrasing. And you should find more than just this pair. So this one here works, but this one here works. And then this one here works. So just kind of scroll along here. And you know what? You could even grab this little one here and that one there. They're also 3 to 1. And that's happening right here too. This one and that one are also in a 3 to 1 ratio, 2 mass units apart. That's good. You don't want just one pair to verify chlorine. You want to find several. More data is more evidence, and we have a higher probability of being correct if we have more data. Cool. That's question A. Question B, what is the M to Z value for the molecular ion peak? Okay, so let's use the information we had. These are both chlorine. One of them is chlorine 35. The heavier one, the isotope peak, is 37. The parent peak is supposed to have the most common isotopes. So what we do is these peaks are in clusters, right? So here's a cluster, there's a cluster, this is a cluster, here's a cluster. To find the parent peak, go to the rightmost cluster, yep, these peaks here, and choose the largest peak farthest to the right. That means this one, and that happens to be the one that's 3 times as tall as this one. This is your parent peak. Sorry, what's my symbol for parent? It's M plus dot. That's the parent peak, and now we need a value for it. I'll go down here, and I got a lot of scribblings down here, but what's this little tick mark here? That's, well, what I got over here? Man, I really messed this up. This is halfway between 160 and 200. There we go, that helps. Here's a 160, here's a 200, I'm halfway. So this is 180. And then right here is 190. And we already said the mass unit's that far apart. So how far apart is this parent peak from the 180 mark? Not 1 unit, it's 2 units. Yeah, that's 2 units. So this is 182. The parent peak is at 182. Right? So there's the 180, 2 mass units over is the parent peak. That one I got, M dot Z. You got it. Okay, propose a chemical formula. Do I have any idea what elements are also here? Yeah, there's chlorine. So let's start with that one. Subtract the 35, because this is the big peak, and there's the little one. The big one is the most common isotope, 35. So I definitely have a chlorine. So subtract that. Let's see. I'm going to borrow, or what's it called? When my kids went to elementary school, they said it was regrouping. So 8, and you regroup it, so it's 7 plus 1. Bring the 1 over here. You got 12. 12 minus 5 is 7. And then you got the 7 minus 3 is a 4. We got a 1 there. Cool. Now let's find out how many times carbon can go in here. Well, 112 can go into 14 once. You got 2 left over. Bring down the 7. And then 2 times 12 is not 12, it's 24. Come on, Dennis. Subtract that, you get 3. So I got C12, H3, yuck, and then there's a chlorine. We should check the math. 12 times 12, every carbon weighs 12, plus 3, plus 35, that's 38. And this is 144. Add them together, that's a 2, carry 1, that's 8. Good, that's 182. Excellent. So I just want to make sure I didn't make any silly math errors. My parent peak is 182. I scribbled all over it doing the math earlier. Propose a chemical formula. I guess you could try and draw this one. This is going to be tough. There's going to be a lot of pi bonds, a lot of rings. You only have 3 hydrogens. It might take a lot of time. Ew, not an exam. So let's simplify it. Let's take away a carbon and bring in 12 hydrogens. So then we have C11H15 Cl. That'd be easier. Let's go after degrees of unsaturation. That'll make it faster to get a correct answer, correct structure, I think. Let's see. Calculate the number of hydrogens possible, which is 2 times the number of carbons. Add 2 more. Subtract. How many do we actually have? 15. Any other elements? Yeah, chlorine, hydrogens, and halides are added. 15 plus 1, but not nitrogen. If there's a nitrogen, we would subtract it. So chlorine is a halide. It counts it like hydrogen. Divide the whole thing there. Give me a little more room. There we go. So 2 times 11 is 22, plus 2 is 24. 15 and 1 is 16. I'll divide by 2. 24 and 16, is that 8? 8 and 6 is 14. Yeah, It is. It's 8/2, which is 4. Ooh. Anytime your degrees are 4 or more, think benzene. It's not a guarantee, but nature loves benzene. It's quite common. So it might show up in your molecule. A benzene ring has a ring and 3 pi bonds for a total of 4 degrees. Structure doesn't have to have it, but hey, you only need one structure. So that took care of all the degrees right away. So let's just go with that. That took 6 carbons. I'm supposed to have 11. So maybe I'll put an ethyl group here and an ethyl group there and a methyl here, whatever. You can do whatever you want as long as it adds up to 11 carbons. Let's see, 6 in a ring. That's 7, 8, 9, 10, 11. Good. It's got to have a chlorine. You can put it attached to the ring. Yeah, why not? You could put it off of the secondary carbon, off of the end. I got all my degrees. There should automatically be 15 hydrogens there. If you have time, you can check them. I think that structure is good. Good, that was part B. All right, letter C asks, what is the M to Z value for the base peak? So I'm just checking to see if you remember what the base peak is. That's simply your tallest peak. Okay, so they want the M to Z value for this thing. So go down here, and like I said, I really marked it up. This is a little tick mark underneath the x-axis there. So this is the 180, halfway in between. This is the 170 mark. And if I go back, this is 170, this is 169, 168, 167. Or double check, starting here, 167, 168, 169, 170. Yep, right on the little tick mark, little marking there for 170. Good. I got 167. Hopefully everyone else will get the same number. D, what can you say about the peak at M to Z 185? It's little. No, that's not gonna get you any points. Sorry, little humor there. What is gonna get you points? Where is it really? Okay, here's my 180 mark. And this is 190, so halfway in between. This is a little peak. It's that smallest one right there. Okay, what do we know about it? We're looking at structure. We're looking about elements present. Well, okay, the parent is right here. That had the chlorine in it. And then it's not twin. What kind of twin? The other parent peak with the higher isotope, chlorine 37, is right here. And we're 1 mass unit heavier than that. Well, how could it be heavier than the parent? It also has to have an isotope. So what can we say about the peak at 185? It contains the heavier isotope of chlorine, right? So the parent peak was at 182 because it had chlorine 35. This peak right here at 184 has to have the chlorine 37 in it. And now we're after the peak 1 more mass unit heavier. So it needs 1 more isotope. And we know that there's carbon here. So maybe instead of the normal carbon 12, right, we've been multiplying carbon, we've been dividing by 12 because carbon weighs 12 mass units, at least the most common isotope. But the heavy isotope, 1 more mass unit, is carbon 13. It's useful for NMR, but it's pretty rare. Only about 1% of the time does it show up. Or that peak is still a chlorine 37 isotope and maybe deuterium, which is the second isotope of hydrogen, mass 2. Most hydrogen weighs 1 mass unit. I don't know where I got it. Anyways, hydrogen, normal hydrogen weighs 1 mass unit, but deuterium has a neutron in it for 1 more. It weighs a total of 2 mass units. That's what you can say about the peak of 185. Lastly, hey, propose a structure to explain the peak at M to Z 91. So you can go and find it. I think it's this one. Pretty large peak relative to the others. Not as big as that peak, the base peak, but hey, much bigger than the other one. So it's pretty common. Nature says, hey, whatever the molecule look like, this is a pretty stable fragment. It's either a resonance stable carbocation or a resonance stabilized carbocation, because you can't see the free radical. Never mind, you can only see the ion. So it's some type of stabilized carbocation, maybe tertiary. So let's just go after it. Just divide by 12 again. Oh, wait, the parent has 11 carbons, 15 hydrogens, and 1 chlorine. So maybe the peak at 91 has chlorine in it. No, it doesn't. If it did contain chlorine, then this would be in a 3-to-1 ratio with another peak 2 mass units away. So if you go larger, 91 to 93, nope, I don't get a peak that's 1/3 the size. I'll go backwards to 89, nope, I don't get one that's 3 times the size. This one doesn't contain chlorine because this peak does not have another peak in a 3-to-1 ratio, 2 mass units away. Okay, so you get partial credit for saying something like that. Or you could just say, hey, Dennis, it's mass 91. If I divide that by 12, let's see, 12 times 7 is 84. That might work. 12 times 8 is 96. Nope, that won't work. It is 7. 84. Subtract it. That's a 7. So C7H7. So if I said, it looks like it's probably C7H7, now you're telling me there's no chlorine there. So good job. But you need a structure. So draw something that's C7H7 that can stabilize a carbocation. And in fact, just remember this is a fragment. So it's not the whole molecule. It's actually, there's going to be a carbon missing a bond. Or in other words, there's a missing hydrogen here. Let's count the degrees of unsaturation. And if you forget that's a fragment, you might get a weird answer. And let's show you what the weird answer is. Count up the degrees of saturation. So 2 times the number of carbons plus 2 more, minus the actual 7. No adjustments. There's no nitrogen. There's no halide. Divide by 2. 7 times 2 is 14 plus 2 is 16 minus 7. 16 minus 7 is 9 over 2. And that is 4.5. How can you have half a degree? Yeah, there's the error. So if you ever get half a degree, you know you did something wrong. Technically, I guess we didn't do anything wrong. Kind of. You just have to remember this is a fragment. So what you can do is say, hey, let's make it a complete molecule by adding another hydrogen and see what the molecule would look like. Not another carbon, another hydrogen. There we go. Add another hydrogen. And then we calculate the degrees. Still 2 times 7 plus 2. Now we're going to subtract 8. Divide by 2. And then that's 16 minus 8 over 2. That's 8 over 2, which is 4 degrees. I suspect a benzene ring. Oh yeah, because molecule had a benzene ring. But there's 7 carbons. So it's not just a benzene ring. It's going to be these 6 carbons of the benzene ring, and then the 7th one here. And then let's count our hydrogens. I'm going to keep all the hydrogens on benzene. And I'll put the carbocation here, so it's benzylic. That's resonance stabilized. This pi bond can move over here and put the plus charge on this carbon, and it can go around the ring, stabilize it through resonance. Hey, if this carbocation exists, then this carbon can only be making 3 bonds for a total of 7 H's. There we go. That's the structure I was looking for. There's another one. I think in the answer key, it suggests what it is. We'll see it again next semester too. We're done with number 10. Yeah, Try to think, is there anything else I want to say? Nope. All righty. After 10, I chose to pick 12. Okay, this one has to do with the depth NMR. Predict which carbons will appear in the depth 90. Okay, so you have to remember, maybe that's why I chose this one, just to remind us the depth 90 is only producing peaks when carbon has one hydrogen. The 135 will give you a positive peak if you have odd numbers of hydrogen on that carbon. So either one hydrogen or 3. You get negative peaks if you have 2 hydrogens on the carbon. Okay, so what you can do, oh, ibuprofen, cool. I would get out skeletal drawings and just carefully put in your hydrogens, because you need to know how many hydrogens are on each carbon. So I just copied it down here, but you could draw right on this structure if you wanted to. We're at the end of the chain, so that's a methyl. This carbon, I only see 3 bonds, so there's a hydrogen here. This one has 2 bonds. There's 2 H's here. This one, I see all 4 bonds, no H's. There's only 3 H's here, and sorry, 3 bonds here gives you 1 H. Same with the other side. This carbon, I see a double bond that way, single bond over there, and another single down here. That's a total of 4 bonds, carbon bonds 4 times. It's done. This one needs a hydrogen. This is a methyl. Hey, and there's a hydrogen, but this is depth. You're only looking at the carbons with H's, so ignore the alcohol group. That's not alcohol. Ignore the carboxylic acid group. All right, what are we supposed to do? Predict which ones will appear in the depth 90. So, you want to be clear in your answer so I can give you all the points you deserve. So don't be too sloppy here. So maybe we will say, let's circle it. And just tell me what you're going to do. It's circled. So how many CH groups we have? Well, here's one. There's another one. Here's another one. Here's another one, and another one, and another one. You get them all? Yeah, that's it. Okay, so that tells me clearly, I think, handwriting's a little bad, but I can read it. So try and just do a, no worse than what I did there in terms of writing, so I can figure it out. Yeah, the depth 90, CH only. Okay, so then maybe put a plus sign. When carbon has 1 hydrogen or 3 in the depth 135. Okay, so it'd be this one. And this one again, the CH, and then the methyl. It's a plus, here's a plus, here's a plus, there's a plus, everywhere plus, plus. Yeah. And then the methyl I missed. I think we're good. And the negative one is a CH2 group in the depth 135. And that's right here, this carbon with those 2 H's. There's a carbon right here they have not identified, and that's fine. This carbon does not produce any peaks in the depth 90 nor the depth 135. It has no hydrogens. And same is true for this carbon. Everyone else has hydrogens. This one didn't. This has no hydrogens. And we're good. We're done with number 12. Nice. Well, now you could use depth NMR spectroscopy to differentiate between 1,4-dichlorobutane and 2,3-dichlorobutane. We're looking at the depth 90, and again, more points for more details. So depth 90, we can go up here and look at our discussion. Depth 90 looks at CH. The depth 135 looks at the odd number of H's, gives you a positive peak, also tells you negative peaks for the CH2 groups. You also have the regular broadband decoupled, but this is all depth 90, sorry. Oh, carbons that do not have hydrogen do not give peaks in the depth NMR experiment. So those are some of the details you can use as you describe how these two molecules give different or have different data in the depth NMR. So here we go, 1,4-dichlorobutane. Let's see the H's so we can count them. See how many carbons possess hydrogen and how many of them. So butane, I'll write out my C's. 4 carbons, butane, Molly eats peanut butter. On carbon 1, there's a chlorine, and on carbon 4, there's a chlorine. And then we just have hydrogens everywhere else. I'll put this like this. And that's an H, and that's an H, and that's an H, and that's an H. Hey, there's a symmetry plane right here. Okay, so that means these carbons are equivalent, giving you one peak. CH2 group, that's going to be a negative in the depth 135. And then this one is also a CH2 group. It's also going to be negative. Same is true over here and there, but you know, the carbon that produces a peak here will have its peak at the same position as this carbon because they're symmetrical. Alrighty, what about the other molecule? Well, it's still butane, 4 carbons in a row, but on carbon 2 and 3, you have chlorine. And then that's all we know. So this is a CH3 and that's a CH3. And this has an H and that has an H, and carbon makes 4 bonds and another plane of symmetry. So then this CH is going to be in the depth 90. Oh, maybe I'll circle it. That's what I did in the other problem. And this, and it's also going to be a positive in depth 135. And this one's going to be positive in the depth 135. Oh, wow. So there's a lot of differences. So then you're just saying words what we just mapped out here. You might say like 1,4-dichlorobutane has 2 negative peaks in the depth 135 and no peaks in the depth 90. That's going to be very different from 2,3-dichlorobutane, which has 1 peak. That's a 1 in the depth 90. Right here, there's a CH group, and 2 positive peaks in the depth 135. Okay, so that gives you plenty of detail, full credit there. I don't think there's any other data to pick out of this. Yeah, we're good. 14. Okay, so instead of depth NMR, now let's use hydrogen NMR. In some ways, this is easier. Other students say, no, it's not. The CH, no, and the negative and the positive peaks in the depth NMR is easier and so forth. So it just depends on how your brain is wired. But take a positive look at this. For hydrogen NMR, there's more to look at. So if you compare like the depth 135 and they both have negative peaks, well, then you kind of have to look at the depth 90 and you can't look at much more than that. But for hydrogen, there's 4 things you can look at. So the 4 pieces of data in the hydrogen NMR are the position of the peaks, the number of peaks. Oh, we should talk about what these stand for. Position indicates the functional groups. Go to the correlation table to help you identify functional groups. Number of peaks gives you something about the equivalent hydrogens. We're looking at hydrogen. Number of peaks, what else? Integration That's the number of H's that made the peak. And then maybe the most important detail is splitting, that tells you about neighbors. Okay, oftentimes you can differentiate or distinguish between these molecules just on splitting alone. So usually I look at that first. No, maybe sometimes I look at position. Maybe I pick out the functional groups first. So if I look at A, there's an alkene there and a cycloalkane. This is just alkane. There's an ene in here, an alkene. So I might think about position first. So what's the difference between alkanes and an alkene? Where's my correlation table? Over here? Over here. That's for IR. I want for hydrogen NMR. Here we go. Alkene, where are you? It's called a vinylic hydrogen. Hydrogens on the double bonded carbon show up between 4.5 and 6.5. That's way downfield. The alkanes are right in here. No higher than 1.8 on average. Remember, kind of don't put a whole lot of confidence in the correlation table, but this is pretty good data. 4.5 to 6 is very different from these numbers that are way upfield. So that might be enough. I think it is. So you might say, for A, alkene hydrogens, alkene H, because there are hydrogens on those alkenes, on that alkene, there's just one alkene. Up here at 4.5 to 6.5 on the delta scale or ppm. Alkanes around 1. You could go back to the table and pick out some range. I don't know what it said. I remember 1.8. I don't remember anything more than that. So if you want to, you can grab these numbers. And now primary alkyl group is 0.7 to 1.3. Secondary, if you want to write all that, you can. Or just say, hey, the alkanes are typically between 0.7 and 1.8. That'd be enough, 0.7 and 1.8. So alkanes between 0.7 and 1.8 on the delta scale. That's supposed to be the Greek letter delta, and that's enough to allow you to see the differences there. You could also done splitting, maybe. That's harder. Actually, I don't see much differences there. This next one, though, you have both of them are ethers and alkanes. So position probably is not going to help you. You have the same functional groups. So now look at splitting. And I'm looking at this one because these hydrogens, they look next door and there are no hydrogens next door. There's no neighbors. That's a singlet. For this methyl group, those H's have no neighbors. They're going to be a singlet. But all the hydrogens here have neighbors. So that would be enough. You probably should go in and say, okay, there's 2 H's here. So these hydrogens have 2 neighbors. It's going to become a triplet. And then how about these hydrogens? What kind of peak do they have? Well, no hydrogens on their left, but on the right, there's 3 H's. They're going to be a quartet. Okay, so this molecule produces a quartet and a triplet, whereas this one has a singlet and some other splitting. So that'd be enough to make the difference. And I guess more points, you might have to go in and label these. Okay, for these hydrogens, there's an oxygen here, not a neighbor. Over here, there's 2 H's. That's going to be a triplet. For these hydrogens, there's 2 on the left and 3 on the right. That's a multiplet. It's going to have 5 neighbors. I know 5 neighbors makes it a sextet, 6 peaks, but anytime it's 4 neighbors or more, just call it a multiplet. And finally, these hydrogens have 2 neighbors. That's going to be a triplet again. Oh, and there you go. If you see, yeah, the quartet, that might be hard to tell a difference between a multiplet, but you could look for it. But definitely the singlet is very different from a quartet and a triplet. That's the best way to tell these apart. Cool. I know we could do the others, but check the answer key. That's the main idea. Look at position and splitting, and you can even go after integration. That can help too. For example, I scribbled all over B. So let's redraw it. There's a plane of symmetry there, but not on this one. So, so we can actually use number. These hydrogens are the same as those, and these hydrogens same as those. There's 2 peaks or 2 signals. Signals. Spell signals. Whereas this molecule, there's a peak here, 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 and here. There's 4 signals. We kind of hinted at that. The quartet and the triplet is 2 peaks, 2 signals. And then this molecule is singlet, triplet, multiplet, and a different triplet. Okay. And then where was I going with integration? Oh, these hydrogens are 2 H's high, and this one is 3. Whereas this one is 3 H's, 2H, 2H, and integration is really not helping. There's 2 H's and 2 3 H's. Actually, the integration is not going to help on that one. That's too bad. Not going to help over here. Let's try to see if there's one where it'll work. I really don't see a good case of it. Yeah. Go with splitting and the position. And if you like numbers, that works too. 2 signals versus 4 signals. I'll have to go and look at the answer key if I ever used integration to differentiate between molecules. Number 16. Propose at least 3 structures that satisfy the following spectral data. So what am I looking at? Is this mass spec, IR, carbon NMR, hydrogen NMR, or depth NMR? Well, the scale starts here and increases to 4,000. Oh, that's a good clue. So you could go to the correlation table and say, hey, any numbers around 4,000 in any of these charts? Well, not 4,000. Well, it's pretty close. There's 3,650. Yeah, this is the IR. You see at the top of it, there it is, IR. More importantly, though, these peaks are upside down. This is the IR, the upside down peaks. What spectrum is this? Well, it's counting normally low numbers up to high on the right. Got like a bar graph with clusters. Yeah, this is the mass spec. And you can analyze either one first. Your choice. I'm just going to go top to bottom. Okay, for IR, we pointed out the correlation table. You got it. You can go ahead and use it. I like to do things a little quick and easy, a little quick and dirty. Not dirty, just quick. I guess you can lose some data, so maybe it's quick and dirty. I first check around 3,300. That's around 3,300. I don't have any peaks. So that tells you there's no hydrogen bonding. There's no OH or NH. Second place to look is right at 3,000. Anything to the, I know it's not a straight line, but I think it's pretty clear. There's nothing here. There's no carbon-carbon double bond that has a hydrogen. And this could be an alkene or a benzene ring. You almost always have peaks to the right side. That just means you have alkanes, and most organic molecules got the alkane functional group somewhere. Take a look at 2200s around here, and we don't have any triple bonds between carbons or nitrogen. 1700s, a winner. Okay, look how sharp and narrow these peaks are. I mean, you get cut if you touch these. It's like a thorn. This one's like broad, and it's not going to hurt if you touch the bottom of this. It's not as sharp, is what I'm saying. This is broad. It's very strong, meaning it comes nearly down to the bottom. It's even stronger than that one, I think, or at least as strong. Comes way down here. These are medium. They're going halfway down the graph. A strong and broad peak. Let me back up. 1700 is your double bond region. But when it's broad and strong, it's the C double bond O, the carbonyl peak. That's the most important detail to take away from the IR. These are also important because we're supposed to propose some structures. So as we start drawing molecules, you're going to lose points if you put these functional groups into your drawings because the IR says they're not there. So don't include them. You definitely need a C double bond O group though. Yep. All right. So let's go after the mass spec. So look at your clusters. There's a cluster here, cluster there, and here's one here. I shouldn't mark it up too badly. All right. Go to your cluster peaks farthest to the right and pick the largest one farthest to the right. So that one's my parent, my M plus dot peak, radical cation peak. And now I want to measure it. So it's not quite 100. How far back is it? Well, go back here. We can see the peaks. I think this region has a peak on every one except for this one, but I got a little tick mark. All right, so where am I? There's 60, so halfway is 50. This is 45. Okay, so here's 40, 41, 42, 43, 44, 45. Yep. Okay, so this is one mass unit, this distance. Yep, and that's this distance. This is 99, and this one is 98. It's really important to get the right number because if I said, no, that might be 97, that's an odd number, 97, and that would make me think that nitrogen might be here. So you got to be pretty careful when you measure these mass values. All right, divide by 12. Oh, wait. I know I have an oxygen, so don't divide yet. Take out that oxygen because we got to have it. IR says there's no bond O in here. So my formula better have an oxygen. Oxygen weighs 16 mass units. Look at the periodic table if you forget. 8 minus 6 is 2. 9 minus 1 is 8. Then divide that by 12. And was it 7 is 84? So this is 6, which is 72. 10. So C6, H10 with 1 O. And I already know there's got to be a 1 degree of unsaturation. Make room for this. What else do we know? Well, let's go find out if there's more degrees. I wanted more room on the screen, but I don't want to lose this information. I got to make sure my structure's got a C double bond O and none of the other structures. Let's count the degrees. 2 times 6 plus 2 more minus, it's got 10. No adjustment for oxygen. Divided by 2. 2 times 6 is 12, plus 2 is 14, minus 10 over 2. 4 2, which is 2. Ooh, okay. So I definitely have 1 pi bond. That's what the IR is screaming at me. Make sure you have a C double bond O in your molecule. And then we have 1 more pi bond or a ring. What else do we know? None of those other functional groups. There's no more data. Yeah, so there's going to be a lot of right answers. Make sure you don't, well, you're not going to put a nitrogen triple bond in there, and you shouldn't put in a triple bond because you don't have enough degrees for it. You have to include the C double bond O and a pi bond. And if you only have 1 O, then you can't put an alcohol or a nitrogen. So we're good. Oh, you could put in an alkene. Just make sure your alkene does not have a hydrogen. would be legal. Otherwise, maybe we're thinking, well, to be safe, let's just put a ring in there. So what's my formula? It's C6H10. So don't forget the C double bond O. And then 5 more carbons in a ring. Make that an aldehyde. There's one structure. That's got 5 and 6. There's an O and 2 degrees. Good. How about we get a ring of 6 and put the double bond O there? That works. And we got another ring, put double bond O here. And now it's okay to duplicate your functional groups. I got 2 ketones. That is okay because the directions doesn't say anything about repeating functional groups, so it's okay. But I'm missing 2 carbons. This only has 4 carbons. So maybe put an ethyl group here, there, or 2 methyls on the same carbon, whatever. Lots of correct answers. You can get an alkene in here. Let's get a chain of 6. 1, 2, 3, 4, 5, 6. I know I already got 3 structures, but I'm just saying they don't all have to have rings. We could get a pi bond in here. Let's get my C double bond O in here. And if I put the pi bond here, ooh, I have H's. So let's take away this carbon, put a methyl here. Take away this carbon, put a methyl there. There we go. Let's redraw it. Have an aldehyde here. And then we have a bunch of methyls here. This would be legal. This alkene doesn't have a hydrogen. So we're not going to get any peaks to the left of 3000. And that will be consistent with this infrared spectrum. There's no peaks to the left of 3000. So it's a match. I don't know, is that too much work? Maybe just go with the rings. You decide what you want to do. But once you're done drawing your structures, and you only had to have 3, make sure it's still consistent with the data. Doesn't have any of these functional groups, but it has this one. And it has to add up to mass 98. I guess I should have checked that. I don't feel like doing it. I should do it. Set a good example. Okay. Maybe the best thing to do is go look at your structures and make sure it has the right formula. So I got 4 in a ring. That's 4 carbons. Here's number 5 and 6. There's 1 O. How many H's? Well, there's 3 here, 3 here, none there. 2 there is 8. 2 here is 10. And none there. Good, that's a match. And then just make sure this still adds up to 98. 6 times 12 is 72. Plus 10 is 82. And the oxygen is 16. That's 98. Good. It's all good. I know. Oh, wait. Am I really done? Nope. 2 left. Okay, these are short answers. Number 19. Would you expect 2 enantiomers? Okay, what do we know about enantiomers? Sadly, organic chemistry is a cumulative course. Means, yeah, you have to kind of keep remembering old stuff we learned. It keeps coming back. Even next semester, it's a good idea to review the most common ideas from first semester organic chemistry. I'll try to highlight the most important next semester, but anyways, just give you a head start. Don't just reset the brain and say, okay, I'm gonna start fresh next semester. No, carry over what you learned before. So way back in Unit 1, we talked about enantiomers. They're mirror images that don't superimpose. They're incredibly alike. In fact, there's only 2 general ways in the laboratory to tell them apart. One is using that polarimeter in the plane polarized light. I like to think of this light as chiral light. Enantiomers are chiral. And then the other way is to interact or react. React or interact with another chiral molecule. So essentially, in order to tell the difference between one enantiomer, this R2-bromobutane, from the S2-bromobutane, you have to use chiral light or a chiral molecule. Yeah, that's how I think of plain polarized light as kind of chiral. You need something else that's chiral. And if you don't have something else that's chiral, these molecules are identical by any other measure. So you weigh their density, identical. Look at the color, identical. Reacted with HCl, identical. I don't think it reacts with HCl. What can we do? Oh, let's do an SN2 reaction on them. They go at the same rate. Unless you have a chiral nucleophile, then you might see one react more quickly than the other. Otherwise, they're identical in every way unless you work with something chiral. So then the question is IR chiral? Well, it's not another molecule. Does it use plain polarized light? I don't think so. It's just normal infrared light. This isn't chiral. You can't tell the difference. And that's what you'd explain. You just say enantiomers, you can only tell them apart using these two ways, and IR does not contain plain polarized light. Can you use NMR to tell them apart? Well, what is NMR? That's where you shine radio waves on them. Radio waves aren't chiral either. The answer is no. The trick, though, is there's something called chiral shift reagents. So you add a chiral reagent to the molecule in the NMR sample tube. And turns out that the molecules will start interacting and it'll actually shift the peaks of the enantiomers. And because it's a chiral reagent, you get different shifts and you can tell them apart. So it's pretty clever. Anyways, that's beyond what we're going to work with. Just be able to know chiral molecules incredibly alike. You need something else that's chiral. Plain polarized light kind of counts as chiral. Otherwise, the data is going to be identical. All right, given that, what can we say about two diastereomers? And I gave you two examples, but it doesn't matter. If you have two diastereomers, how similar are those? Well, they're fairly similar. They're isomers, but they're not enantiomers. It's only the enantiomers that are really, really hard to tell apart. Diastereomers are different. So there is a chance that they could be different in the IR, the mass spec, the NMR, the depth, the hydrogen NMR. Yeah, they're diastereomers. They're not the special case of enantiomers. So you could expect different diastereomers of different molecules. There's a chance they'll have different, in this case, carbon NMR spectra. They're not enantiomers, and that's what you might want to say. Enantiomers are the ones that look identical unless you use something chiral, but these molecules are not enantiomers. So there's a chance you can see the difference. Okay, I think that ends our sample test. Get some practice, take a look at the other ones. If you've done the sample test so many times, you've kind of memorized the answers, students will tell me that. Then go back and try some of the homework problems. Do the ones, pick up, be selective, pick the ones you want more practice in so you're confident and you're comfortable with doing these types of problems. All right, good luck. I'll see you in the next video.